Greetings, gentle readers, curious fellow earthlings. Today is July 24, 2026. Reading foundations today. We'll be mostly just digging through the rest of this one box of books here and getting to the next one, then next, maybe next time, if ever. Theoretically, probably. It's not unlikely. That's the plan. So the previous episode was about a little talk about single instruction, multiple data, or the approaches to parallelization vis-a-vis the vectorization on the chips. The super-scalar is what that's called. So with regards to like a very wide or vector-wide instructions and then the vector-wide scalar words, the approach here, what's been being considered, is how to implement scanners, parsers then, or recognizers as of something like regular expressions, vis-a-vis LL and LR parsers, both left to right, the L part, and then one rolling backwards from the left or rolling backwards from the right, vis-a-vis the top-down and bottom-up sorts parsers. Then the framework of the vector-wide scalar word is under the consideration of being able to say that instead of a parser, a scanner, working on a byte at a time, so in any sort of high-level language, meaning above the assembler and the machine code, there's the idea that when reading data, a byte at a time, then that's one character usually. So maybe it's not quite one character. If in UTF-8, in this setting of Unicode, there's the accounts of UCS2 in the big endian and little endian, whether the most significant byte is to the is first or second, MSB to LSB or LSB to MSB of the bytes endianness. That's the way to represent a usual byte, or 8 bits makes a number from 0 to 255, and then all the letters on the keyboard fit in that number range. So all in each of the characters are assigned a particular number. It's called ASCII, the American Symbolic Code for Information Interchange, vis-a-vis ANSI. And so now ASCII was Japanese first. So ANSI is American National Standards Institute. But ASCII was originally sort of a Japanese code. And so that's just the idea, though, that it's very common vis-a-vis EBCDIC or like the old IBM encoding. And any sort of way to make code points, which are numbers, to assign into the range and the space of these values. In this case, for a character set, usually enough the glyph map. The glyph is the symbol or the icon or the pictogram, that the glyph, G-L-Y-P-H. So when dealing with bytes in their native layout, there's UTF-8, which maybe has 1, 2, 3, or 4 bytes to represent a number with otherwise in usual coding that would have to fit into 2 or 3 or 4 of these bytes. So then the idea of working with a byte at a time, then when he gets into like the wider character set of all the letters of all the alphabets of the world, Unicode it's called, which has been around for a long time, since Unicode 2 and Unicode 3 and Unicode 4. At some point in time they added emojis to Unicode, whereas before they would be something like just a particular font, like wingdings, if we go back quite a bit further, with regards to how characters are represented by numbers. And then when treating them on a computer, when dealing with them a character at a time, a usual sort of algorithm will read a character and then consider the cases of what could possibly so follow from that, and then also gather as necessary enough memory and information to collect together a word and make a finding. It's got to find is making a finding, and so for what's found of matchings to match, whether they're made matches or mismatches, just don't match here. The idea being that the usual sort of algorithm has got a different things involved, whether trying to find a string that's a fixed constant itself, or to find a matching when it's a given length of characters of a particular class. So the layout considered is something like this. So when you're dealing with a byte at a time, then you have like a big case table or switch case or like if else and all these kinds of things, introduce what they call the branches. And the branches are just any kind of conditions at all. It's the very idea of a flow chart, two different branches on a flow chart, and being able to say if the condition is like so, A, else B. So the idea of the branchless programming is to make it so that there aren't any of those, because when the computer, the central processing unit, has made a pipeline of these instructions, so it's taken apart and laid out a little plan for each one of them. Then when it hits a branch, it's got what's called branch prediction. So if it's right all the time, then it kind of leans that way as well, because whenever it mispredicts the branch, then it has to throw away a bunch of the different work, and it causes a evictive pipeline, it's called. So the branchless is a key thing here. And so whenever it's just loading one character at a time in a high-level language, or for example, loading a word at a time and then splitting it up and then having the branches and these sorts of things, then the idea is that results not branchless, the algorithm. So then the other idea is to work towards the stall-less too. So a stall is when accessing any kind of data that isn't immediately on the chip at the time it's referenced, has to go get it or fetch it from memory. It has to request it over the memory controller with regards to memory type range and these sorts of accounts of the architectures. And so it takes essentially a long, long time to just get one extra value, and then to have that ready to compare or to perform arithmetic upon to result finding the thing. So the idea here with this very wide scalar word is, first of all, is that then the vector registers on the chips are like 8 or 16 bytes wide. So chips these days, if we consider everything to be 64-bit, it's hard to find chips on the market these days that aren't 64-bit in PCs or phones. And now it used to be for a while that phones are still 32-bit, but even these days phones are going to 64-bit. And so back in the 16 and after the 8-bit days and then the 32-bit days, then the registers on the PC were only 32 bits wide, 4 bytes. And then there was only a handful of them, or 6 or 7, or maybe 8 of these registers on the Intel chips. And so then the ARM chips, they have something like 8 or 16 or even 32 registers on their 32 bits, and then there's 64 bits. So when Intel went to 64, and when I say Intel, I mean Intel and AMD, they kind of have played back and forth with each other over what are the successful instruction sets adopted by the industry. And Cyrix, and then there's 3 or 4 or 5 other new manufacturers of Intel architecture chips. According to CPU ID, the manufacturer name, mostly Chinese. There's 3 or 4 new constants in the instruction to find out what those are. But they're all compatible, is the idea, and they all have the same internal organization. And if slightly varying performance and slightly different instructions, they have the same architecture according to the instruction set. So the idea is that you can load onto 8 bytes, this 64 bits, or in the case of 128 bits, this has gone to streaming SSE after MMX is this idea. Went from 64 to 128 bits. And then this AVX went, and then AVX2 went to 512, and after 256. So 8 bytes, 16 bytes, 32 bytes, and 64 bytes. And so the idea is that as those have grown, and then the ARM chips have a similar organization, that they have about the same scale, same number of registers, and then the same width of the registers. And ARM seems having a few more free registers. Yet basically for modern commodity CPUs these days, there's 16 general purpose registers, which are 64 bits. And then there's, or more, but there's at least that many. And then according to basically 3 editions of the vector extensions, there's the after MMX, which was back in the 90s even, and it reuses the floating point unit to do integer operations in the pack sort, the parallel of them. When you just line up 4 at a time, you load up in those 64 bits 4 different shorts, they call them, or 2 bytes together, or 2 longs, to making words and quad words, or double words, double words, and quad words, so words of the 16-bit variety. The instruction adds all those up at once. So if you can get them all lined up at once and then add them, then they all line up at once. And so the idea is then that is faster, because it happens in this, if not quite this one clock cycle. It happens according to the reorder buffer and the pipeline of the mu ops that is decomposed into these instructions this way. So it's faster. It provides linear speed up, meaning it's 4 times as fast than by itself alone, the scalar way. So the idea of then having this is that there's general purpose registers, and then there's the vector registers. So both of the architectures basically separate the general purpose registers, which have kind of a richer, fuller instruction set. It can treat each one of them as like, besides loading and storing, and besides the arithmetic and these kinds of things, it has like to find the first bit set and a couple other different algorithms within the bits mostly. And then the vector registers, while lacking those, they have instructions that enable what's called shuffle and permute in the later editions. That basically across the way there's a function called shuffle the bytes, which provides a little lookup table saying, okay, for each of these bytes, you can associate it with the 4-bit index, and if it matches, you can line it up. So that's PSHUFB, it's called, parallel shuffle B, or packed shuffle B. For byte in the Intel architecture, and they have the very similar thing on the ARM chips called table, TBL, which is actually quite a bit more flexible, because that instruction is rich and enables to make the lookup tables. So the key notion of the lookup table is that you've already pre-computed something for each one of these bytes. So for example, for the first 256 characters in Unicode, among those there's the first 128 of those, and it's usually called ASCII. Now, when you're interested in parsing those, then each one of these falls into a particular character class. So there are basically 4 kinds of character classes. Punctuation, which is any kind of bracket, parentheses, all the characters above the numbers, commas, semicolon and colon, question marks, ampersands, all the punctuation, anything that's just symbolic and not a letter, a digit, or whitespace. So punctuation is a first sort of character class here considered. And then there's the alphanumeric. So the alphanumeric has basically the alphabetical and the numeric. So there's alnum is this kind of class, and then directly underneath that are digits, 0 through 9, and alpha for alphabetical, A through Z lowercase and A through Z uppercase. So then the other character class here is space. And so space, or white space it's called, because on a usual piece of paper where it's printed, it just doesn't show anything at all, yet it was formatted and laid out in the typesetting algorithms that so make it like so. With regards to fonts and kerning and leading and the gutter and the trough and these other terms that come all the way back from the days when typesetting was the actual manual activity of laying out all these different tiny little letters that were embossed with the letters in reverse mirror image, and then stamping them, pressing them on a piece of paper. Fonts and the glyphs as they're so rendered. So the white space is then the idea of this other character class. So there's punctuation, white space, alphanumeric, and then finally this kind of non-printable characters called the control characters. These are called coded. So having a lookup table makes it so that when you load all the bytes up, you point to a memory location and all the characters are just in a row. And then when it makes it so that you want to work on each one of those characters a piece, you either have to kind of split off that tiny little piece, the least addressable unit of memory or RAM, called the byte. That's the definition of what a byte is. It's the least addressable unit of RAM. So it's almost everywhere, forever, 8 bits. As according when you look at the header files of the compilation sources, there's a constant called char bit or char char bit, char underscore bit, all uppercase. It's equal to 8. It's an octet, they call them, of the bits. So the other usual name for byte is octet, an 8-some, 8 many. So and various there was a time when there were computers that had 9 bits in a byte, and they had 36 bits in a word. This is just no longer the case. Yeah, it's possible, and it's according to then the variable length of the fixed length of the multiples of the moduli of the layout of the alignment of all these numbers as they are, according to the register model, the register file of the register transfer logic that moves the numbers on and off the CPU, which has got a little machine that processes them according to a list of instructions that follows the instruction pointer, the machine. So a lookup table is very useful because each of these 256 bits, 256 characters in this range of a byte with, according to bits as numbers as an unsigned integer, that they would have these classes. So when you load up a word that's got each of these bytes in a row, then each of the bytes has a representative of what's called its character classes in this 2 nibbles. So a byte is 8 bits, and a nibble is spelled like byte. The computer byte is spelled B-Y-T-E, whereas like a tooth byte is spelled B-I-T-E. Similarly, a nibble, which is a tooth nibble, is spelled N-I-B-B-L-E. A computer nibble is spelled N-Y-B-B-L-E. So a nibble, it's got 4 bits instead of 8. So an 8-bit byte is 2 4-bit nibbles. So the idea is this character class, if there's these 4 character classes, then they're exclusive. So any one of the characters in the character that's a byte is either whitespace, called white, punctuation, called punct, P-U-N-C-T, alphanumeric, called alnum, or it's coded, C-O-D-E-D, coded. So in that nibble, you can have one of those 4 bytes indicates which one it is. And then when they're aligned and laid out, you load it from the lookup table. This is already just a computed little table. So you tick the number, and you get the code that is this character class, its first nibble, the primary properties of the character. So the idea is that each of these bits in the nibble is an indicator. It's an on-off bit. So it's either on, meaning yes, positive is so, or it's off, and just doesn't say, which means no. And so the idea is that then when all those nibbles are figured out, then these following ones that there are of them are like this. The first one divides characters into, it divides alnum, first of all, into digits or letters. And it divides digits into 0 and whole numbers. So a number is either between 1 through 9, it's a whole number, or it's 0, this digit. It's 0. So it's an alnum digit then has, in those 2 nibbles, then has furthermore whether it's the digit is 1 through 9 or 0. And then secondly, the letters basically have uppercase and lowercase. Those are the other 2 indicators. So capital A through Z are so indicated, and lowercase a through Z are so indicated. And then the spaces are broken out basically horizontal spaces or vertical spaces. So horizontal spaces include tab, space is the first one. And then there's a variety of lesser used horizontal spaces, like non-breaking space. And these don't exist in ASCII, but they do exist in Unicode. So in later trying to make algorithms like regular expression matchers or parsers that would work on such these, then these though are just these primary properties of the ASCII or keyboard characters. So there's horizontal white space, space, and tab, and the vertical white space, carriage return after new line. That new line is the most usual line break element in text files of all the sorts of text data. So trying to address this sort of way of using this very wide scalar word for text algorithms is the setting where all the source language fits in this very limited set that basically sits on the keyboard, and that these are all programming languages that are there really are. All their characters fit in this. Then when they use Unicode characters for whatever reason, whether it's in the sources identifiers or in comments or otherwise just in the setting or as constants, these are there are ways and ways to represent those from when the character set that couldn't include those themselves to these days it's almost ubiquitously the UTF-8 encoded data of the Unicode, because in that setting 0 through 127 are only 1 byte and they're all the same as ASCII. So an ASCII file by itself is a UTF-8 file in this sort of way. So getting then back into why the different whitespace characters would have for matching and so on, and the categorizations of these properties are making these bitwise properties of the characters, and then having that for each one that's loaded up as a byte in this word of many bytes, that each one then has right beneath it on the next register basically this first primary amount of its character classes, and then these second more broken out ways. That then the next two character classes after alnum and whitespace is that the first is this punctuation, which has a lot of different meaning, and because it's structural in all the source languages. And then the second one is coded, it's called, and that includes both these non-printable control characters that aren't otherwise part of the character classes, or when it's a UTF-8 encoded character. So so if it loads up a byte and according to which character set it is, like for example, if it's UCS2 and it's always just wide characters, 2 bytes wide for each character, this would be a different approach, and you'd basically load up doubles of those for these character classes when it happened to be ASCII. The idea being then that punctuation is broken out between commas and joiners and brackets or groupers. So there are basically two different roles of punctuation in these source languages, or three here. So the first role is to join things, like comma. Just like you'd write a sequence of words and separate them with the commas, they're actually joined with the comma while they're being separated. Because otherwise you can just imagine a string of tokens separated by white space or something like that. In that sense, white space is sometimes semantically a joiner or a separator. But here the point is that there are particular elements like semicolon is used a lot as a segment connecting hierarchical namespacing and these kinds of things. Or commas, that it's fundamentally this sort of meaning to what it is. So the punctuation is broken out. The first nibble says whether it's a grouper, which is then the parentheses on the outside, or the brackets, which contain within them some expression or context for evaluation, or like a pair of quotes that string literals within them and these sorts of things. Called outer, and then in the inner side are the arithmetic operations, plus, minus, times, divides, and these sorts of accounts. And then finally there's this third character class that's a subclass of its primary character class for punctuation. Is the affix. So there's inner, outer, and affix, which is basically on the front or the back. So it might be considered something like if a minus sign in front, except that's already used as a minus sign in arithmetic, or the idea of a hash sign like leading off a comment for the rest of the line, or otherwise that's just another kind of punctuation. Unary, say, like with regards to prefix and postfix, is affix. So three of those character classes basically then has that all the source languages are just strings of or sequences of the alphanumeric, the identifiers, and then the keywords, which are fixed constant strings reserved in the language for no other purpose, yet for their account of being keywords in the language. Then there's whitespace, which is usually just cosmetic, meaning it's insignificant. There's just a white space to separate two identifiers. It doesn't otherwise say how much white space it can or can't be, or what kind of white space it can or can't be, vertical or horizontal here. The idea being, though, that usually it's insignificant. Some programming languages actually use white space as significant in their structure, in the layout of the sources. So this would include examples where indentation basically make nesting, and then everything within a given indentation level is the same block of statements. In all functional languages, in all procedural languages, in these sorts of accounts, the procedural elements are laid out in blocks. And then with regards to like nesting languages that are entirely so hierarchical, again, it's all blocks and nesting and blocks of statements. And eventually it's after lines of statements or statements themselves. When there are multiple statements on a line, all being in the same block, that identifying scope and these kinds of things. This is much, much higher up in the grammar analysis, in the semantic analysis, than what this is to begin as just providing these bits are the properties, and then they're computed, and they indicate what would be so for predicates, a true-false sort of relation on one of these kinds of things. So given one of these bytes, you can read off the first nibble and find out what character class, and so if it's alphanumeric, it's indicated. And if it's digit, it's indicated. And then after the second byte, the secondary characteristics that kind of fills it out a little bit more. And that could be according to various modes or what's relevant to later the expressions that are used to get building up these sorts of ideas. Has that the bits thusly are aligned underneath the character. So the code point, the character's number itself, and then these primary and maybe these secondary bytes are in a grid. They're in a lattice of these things. So that then, when looking to make matches or findings, is that basically the algorithm here is being first about finding. That find has find longest match or find nearest exit, I'm calling it, which is like acceptors, as long as it matches, keep matching, and rejectors, as soon as it doesn't match, quit matching. So this is the account of when it's the variable length, the expression, like finding the bounds of an identifier or something like that. Or then for the fixed length, that it's pretty much, it's a different kind of case, because you're not comparing on the character classes necessarily. You're just comparing it to the code points itself. So if it's CAT for cat, then you can just load up another register with CAT for cat and just shift it along that string until when you XOR them together, then the only bits that will result in that being 0 are those matching. That the 0 is the indicator of a match in this particular case. So going back from when that's kind of specialized its own way, matching fixed strings in a multiple byte word, because then this all happens inside the CPU, see. Instead of that, in a higher level language, it calls in, it gets one. And then as it's compiled to assembly code, it's got different branches in this and branches in that. And each time it's making a fetch from a memory location to find out what this next one is and bringing them back and forth, and these kinds of things. So the idea is you load up the register word once, you load up the table, and that's an expensive operation called gather, because you have to gather from this table each one of these bytes and lay it then into place. And that's simplified in some of these register settings because the instructions they have, again, are limited compared to the general purpose. And then here, what I'm calling the general auxiliary methods of like the MMX registers, the old parallel, where it's given kind of that the old parallel and the general purpose register sit on one side, and they're doing the logic and having the state of the machine, this very wide scalar word machine. And then the vector registers themselves are being filled and laid out as full as possible, moved as little as possible, and then acted upon as expedient as possible. So this is kind of the idea. Now, why this I'm finding interesting in this descriptive detail is Abstractly, it's just a model of a machine, but mostly because I don't already know where there is one. And so I just expect them to be everywhere. I expect to be so common and bog standard that having a general approach to these sorts of things would be like so, because all the commodity CPUs these days have these vector registers. And it's relevant to use them because they operate with a linear speed up. And for when scanning and parsing things, like when having an email service and like reading the headers or an HTTP or any kind of service and working with internet messages of the usual sorts, other commodity standards that have been around forever and are used for everything, that it makes kind of a lot of sense to have that, which is its inner loop or inner routine, be this way. So the idea then is to have the register words, and then when looking for matches, then instead of having a parser generator, they call them, it will usually make something what's called a DFA or NFA. It's in its form what it does. This deterministic finite automaton or non-deterministic finite automaton, which is surprisingly is that a non-deterministic finite automaton actually has a relation and a representation as a deterministic finite automaton. I'd use a different kind of word than a non-deterministic finite automaton. I'd probably call them a super deterministic automaton, an SDA, instead of the non-deterministic. Point being, this is the model when there's only one byte at a time to read, and then it can follow the tracks in its state machine. That it's got a state machine, which is a very common and regular way to describe that a given process is in a given state, and then it's got transitions from that state according to events, just like the flowchart and the branches going from one to the next. And then according to that, it's well defined where it is in this state machine, as with regards to state machines and stack machines and the like. So here the idea is that the bookkeeping of the offsets and what results, this layout of the a layer after the sequence of the source code and source text itself is then to be finding the offsets in the passive tokenization or scanning of this thing. So then this is described formally in terms of these DFAs and NFAs, or as they were. And then there's accounts in the grammar of the regular languages, which can be matched by a regular expression. And according to formal, it's called formal methods and formal languages and formal automata. And then the grammars, which are these, for example, a regular language or a context-free grammar, which can always be just broken off byte by byte or character by character, and it always results the same tokenization, breaking up the source text via segments, these empty strings that connect the whole thing together. Then there's context-sensitive grammars, which involve having to reread or backtrack more thoroughly, and otherwise make an account where it actually matters when two different symbols are part of a language, that they would have different significance. Like all natural language is contextual grammar. So somewhere between those two, there's a context-free grammar and then like a context-bracketed grammar. And this basically has for the accounts of balancing of nesting of brackets or parentheses, that it's possible to write to that and not need to make an account for all the equivalency results of all the theorems of formal methods. What machine can parse what language, what kind of capacity a machine. There's at least a third kind of grammar that fits between those two, that covers a lot more what's usual relevant. Disambiguation, for example, when two angle brackets is a shift operator, or when two angle brackets just happens to be a nested immediately brackets, these sorts of things. That this sort of context bracketed language right above a context-free language is enough to make for almost all sorts of source texts a unambiguous representation of the results of its scanning or lexing or making the lexemes of the tokens, of the tokenization of implementations like the string toke function to break a string into substrings by a delimiter that's omitted, or the regular expressions, which are intersections, unions, and set minus or complements of different expressions that indicate acceptors and rejectors, and then all those put together that would match any, or would make a finding of any kind of string, whether it has a matching of any kind of string, and then where it does, with regards to then how it does, and then that being usually into search and replace and these sorts of accounts of the capture groups and the transformation or substitution. After search and replace, there's substitution more generally in regular expression engines. Here, though, it's just about the read-only aspect and building up this after the sequence of the source text, then these layers that follow it along and make for so that there's this machine defined to work on the commodity computers that happens to fully employ as much as possible their resources, and so it would be faster is the idea. This is an account of making something that would be as fast as it possibly could be according to what instruction operations there are, the resources. And I'd look for something like this, and there's lots of different accounts of parallelization, and it vectorizes my loops. The compiler just optimize it. It does, and that's a lot of times for simpler cases where it's like, oh, you just want to add up these three tuples. They're already organized as like bytes in a row, and so just you want to add x, y, and z components and maybe w, and call that a sum, like a column sum, just like FORTRAN would describe it in terms of arrays and stuff with regards to the various differences, similarities, but differences in the arrays of FORTRAN and the arrays of C, what's column major and what's row major in these sorts of accounts. So anyways, the instructions are sitting there, and they're widely used for these sorts of things, or for graphics processing. Within the deep within the heart of all the graphics processing are all these 64-bit blocks, and they're being computed by the CPU as fast as possible to make videos and all sorts of things that these vectorized or parallel instructions originally called like the multimedia extensions with regards to AltaVec or 3D Now and these sorts of things, indicating by their names what they're meant to provide, which are enough resources to make it possible to have higher performance graphical operations, or the matrix multiplication, or the accounts of computing quaternions or something like that. That they're aligned, but they're just kind of parallel packed units that they just do a super-scalar array of these things at one time. Sometimes with the instructions being able to be horizontal vis-a-vis the vertical instructions, the idea being having two registers, and the vertical instruction says, and now in one of those or in a third register, compute their sum, or perform the binary logic of and, or, here IOR for inclusive OR, XOR, exclusive OR, or then with regards to NAND and not, a little bit less in this case, but and OR and XOR, the logical operations straight down the vertical. Then the horizontal is able to take some of these accounts of like the shuffling or the blending, where it, for example, moves some bytes from left to right. And this is then a little bit different than the usual idea of shift and shift and rotate. They actually just spin all the bytes in the whole register around. So those kind of sit up above are shift and rotate. Then there's and, or, and XOR, the logical operations. And then there's these various accounts of just packed arithmetic down each of these lanes, they're called. Given a vector is split into given so many lanes. For example, 64 bits, the vector with two 32-bit floating point elements in them, singles. Or one with 4, or with half floats, or with bytes here. Everything here is just bytes, and they're unsigned integers. It's the usual kind of account. That all these instructions were built after the floating point unit was built in 3 to 6 to actually just compute floating point numbers fast because multiplication and division are slow and slower in these sorts of accounts. Then later it was used for the graphics accelerators. So these are just called, besides accelerators, these are the accelerators and these sorts of things. Besides like just having extra RAM and these sorts of accounts. So for these text algorithms, then this very wide scalar word is this sort of architecture where it's figured to just load up data, whether it's source text or later the different courses sort of focus on that is on the spoken word text. So for text data, there's source, which is computer sources or data files. And figuring those again are parsed very, very rapidly by this sort of account. And then there's spoken language, which would include and have different roles of the productions of the grammars and these sorts of things, yet as well have the same kind of orientation. Similarly, for binary data, then that's loaded up, then with regards to the fixed width and the variable width, or the fixed length and the variable length of the codes. Here, for example, when it's discussed that all these things are bytes, and so they're fixed length, then when the UTF-8 character it's encoding, or the code point it's encoding, has a given number of bytes, it's variable length, then trying to figure out how to handle that is a common problem that most systems solve by unpacking everything into fixed length. So that, for example, there's just considered, well, a character is just a byte, or a character is exactly 2 bytes, a wide character. Since the days of internationalization and Unicode being put on the commodity operating systems, with regards to, before the Unicode, there was dozens, several dozens code pages in effect. The Windows code pages for each of the different languages, which and their collections of codes, which in Unicode are called planes, and according to general classes, what language they come from, and these sorts of things. That being like code page 1252 on Windows for EN/US, English, American, and these sorts of things. The language codes. So that then all these different encodings called character sets. Then and they're legacy obsolete ones for Russian and Koi and Han and Big5, the Chinese, and Shift-JIS, the Japanese, and a lot of these different sorts of accounts vis-a-vis all the different Euro languages, basically following as after ASCII. They just used the letters, the numbers from 128 to 255. And then today that's just almost always called ISO, International Standards Organization, 8859. It's a series of the specification of standard. 15, because the first one was 1, and then for 15 they removed one unused character and they added the euro sign, like the dollar sign of that currency. So that's always it's a 1 byte fixed length encoding. And then the other multi-byte encodings and the multi-byte variable byte encodings mostly point to Unicode these days. So with regards to handling binary data, then the usual codes, whether they might be markers or segments, and they're bytes, and they're at fixed offsets and these sorts of things. With regards to headers and structure, and the states of the recognizers or parsers that would be for reading files, then there's the idea then that those being variable length codes then also have the same kind of idea across this vector wide scalar word, because just considering the entire thing is just data in a row that can be segmented and chunked into bytes, and that's basically then there's common operations among the Intel and the ARM with regards to the what's called SSE 4.2 and AVX2 and AVX-512, and then this little bit later thing on Intel that hasn't quite arrived yet. The count of how many and how wide the registers are and what instructions they have in common. And then on the ARM chips, and if this is all 64-bit architecture, all of these, then they have this kind of the same outline of their organization and dimensions and sizes of the registers and the structure and organization of their operations, that there's a common subset between them that works the same on both of these architectures, or any sort of architecture with these sorts of extensions for these sorts of vector operations. For example, as like MIPS RISC-V or something like that. It's just not different, is the idea. So, and that's without getting into the idea of something like ARM's scalable vector extensions, where they're saying, well, you know, we just keep adding width to these vectors. Let's just say we don't need any more and just use the same instructions, and it will just use the whole vector, however wide it is. And then you can parcel that out among various different kinds of like vert users and stuff like that for a bunch of these different ideas. So the machines, the CPUs are the same, the abstract models of them. And then the machine, the algorithms go into these findings and matchings are also the same. And they're just driven by data. Because then what happens is there's matched up a word with the properties. So there's the properties are derivative of the input and data, and they're computed and derived. The properties accumulate on the data, the source data. It is the source file. The locator points to it at its location in bytes. Okay. So then the predicates are what you are looking to find or match. So the predicates are saying, oh, well, I'm looking for the alnum bit that's 0, and that's the alnum bit that's a digit that's the 0 bit. And so I know that there's a byte that I need to match in the that it's got to be alnum and a digit, and then a byte to match, and that it's the 0 in this case, for example. And why that is basically to separate 0 from 1 and 9 is, first of all, there's just a half nibble left there, and it's not being used for anything else. And secondly, it's an exclusive class. Any element in the range 1 through 9 is not in the range 0, and vice versa. And finally, it closes the class. Like those 2 bits is like everything in that whole category is assigned one of the 2 of those values, those indicators. So you got all those properties, then you just line up the predicates, you just make those match. And then and those together, XOR those together, say, and then the only places that match will have a matching bit. And then you can use something like what's called saturating multiply, although that's to be figured out because it's not present on the Intel chips. Or maybe some kind of the shuffle, or otherwise the instructions that there are in the registers, because there's not really that many, and so they're few, and yet they're fast, and they are the resources to use. So given this, then you can use something like this. It's called packed move mask B. Take a list of bytes, like these 64 bits. They're 8 bytes in one of these registers. And so this instruction is implemented all the way across these things. It's the same instruction. Then that will take those 8 bytes and take the high bit off of them and put them into 8 bits. So now when you're looking across the order from 0 to 7 of these bytes in a row, this string, and now you have a byte with the bits in it between 0 and 7 of what matches and what doesn't match. So instead of doing like if this expression, if my mask with this, or like if this character is between 1 and 9, or if this character equals 0, and then if else, and then jump, and doing the conditional logic or the branching, it just always computes all of them at once, because you're gonna do that anyways. You're gonna evaluate these sorts of predicates in the parser and the scanner, and these are the character classes to begin. So then what results then, the algorithm to find the first bit set, it's called find first set, or bit scan forward. And then it returns like, well, at index 3 is where cat begins. And or in index 3 is where there's a 0. Or at each of these bits that's an on bit, that's where the 0 is in the example. Excuse me, the 0 here is just an example of matching, or making a finding for these things. And so when building identifiers or looking for different kinds of characters that match, you can just match any one of those. Taking the union of the character classes is that if any one of those bits is set, then at least one of the bits is set in the resulting evaluation of the predicate by logical operations. Then you multiply that by a given number so that no matter which of the lowest bits of those is set, as long as none of them are 0, it will result a full byte, OXFF or 255. All the bits are set. And then this pmove mask B will shrink that to a byte where in order they're all set. And then the bit scan operations work on those. And there's 64 of those across. If there's 64 bytes of input, now it's got 64 computed indicators matching or not across. And then that's a way, then just find the first of those. Find longest match. Then with regards to then find nearest exit in case any one of them doesn't match, then that's also where it doesn't match. Another way to consider that is like, well, because you might say, well, there's no difference between those two, find longest and find nearest, because they're being evaluated out that way. But if you imagine that you got 64 bytes and you're like, go do you find a line ending, because then you might just want to start at the back, and then so the find longest match kind of starts at the rear and then rolls the other way. And so in this case, there's find nearest exit and find longest match together, and then they can pass each other and result that they never do is the idea. And then that in this way, in the cases where you're looking for the find next or find first is when you expect it to be, there is always just a next token, or I don't know how far away it is to look. It does both is kind of the idea. And when it's basically to be made it so that that's happening rapidly, when you want to be scanning forward to find that next line break as fast as possible, because you're ignoring all that data, but you got to load it to look, is that when the data gets loaded, then the mask to match it can just be computed as it's rolled or shift off there, and then the arithmetic results that just accumulates and saturates, and then it either matches or it doesn't. So these are the sorts of accounts of these things. So I'm making one of these, and this is kind of the way I'm going about it. And then it gets involved in a number of different ideas about how to handle character encoding. So the first idea of this coded class, so there's punctuation and whitespace, and there's alphanumeric, and then there's coded values. So these are like the control values of the control characters they're called, like Bell or the lesser used matters of the TTY or teletype interface. The control characters they're usually just banned from any kind of source text because they're non-printable. They're called also the non-printable characters. And that they're just considered coded. So if they exist in the stream, they're just considered like so. Or it could be like coded 0, like the 0 value in a UCS2 character or something like that. Again, that's sort of starts getting into the big difference between 2-byte character encodings or multi-byte character encodings and single-byte character encodings, and the variable length character encodings. We see the character sets and the character encodings of the code points or result the glyph maps and the various control characters or the ligatures generally, the organization after left to right and mirror symmetry and these sorts of things, but mostly the connecting of different glyphs together. It's just all called ligatures, like AE smashed together and made E, or FI smashed together and made one typeset character, ligatures. So then the coded characters then get involved with how to match these strings when you're matching to the character, not just that byte anymore. But you want it to match by having a bit mask that is then you can shift along, and then logic and arithmetic, the CPU computes it in a constant time with that's branchless and stallless is the idea, which it can do. So then the idea, this gets involved into a number of different notions about in this case about the variable length and how to handle it when you want to deal with the aligned grid and lattice of the words. So you can use the arithmetic, the vector-wide arithmetic to compute it, is to have it that that is called smearing and smashing. So smearing is the idea is like, well, this character that I'm looking for to match is just the character's value. It's according to a character class, not necessarily the byte that among several of those makes a variable length of bytes, an octet sequence, the code point's a code point, and these kinds of things to have one character. So the idea is like, well, I've had this indicator bit here, and it reaches to where that character range is coded and continues. Just smear out that indicator there, because then that will result when you do the arithmetic, the logic, it will just output that those 3 bytes are match or not match according to the character class, because the character class is the same for all these things, and not just these primary and secondary character classes of ASCII, the source text, but all the Unicode character classes, all the POSIX character classes. They have other lookup tables if you're going to employ them in the expressions that make these then just a token, a machine word to add up there and have it be computed automatically. There's just this breakout of these things. So the smearing is to spread the bits out, and then as it goes along, is shifting and rotating the mask to march it back and forth to find where it starts and ends when you're looking for a specific combination of patterns. That this is the primitive sort of finding that happens where it is like so. And then smashing is the idea of kind of like, well, it's got 2 bytes, or it's got 1 byte, smash it out into 2. Or it's got 2 and smash it back out into 1. So the variable length is described here in this variable or vector-wide scalar word is by smearing the matching area, so then the logic is the same, or smashing it with regards to saying, well, we're going to take these 2 coded characters and they happen to make 1. Like we want to do some collation or something like that. Or this A with the accent by itself just acts as A in the letter in the alphabet when we want to have collation and sorting and these kinds of things with regards to matching and then comparison and these sorts of things. To have it like so that then any sort of text input, it can be kind of agnostic to character set, except according to loading these relevant character classes according to what they are. Yet aware of the issues involved with variable length and the multi-byte character sets, and that it's all kind of built in. And particularly here, kind of that it never has to modify the data to load it up. So if you have a gigabyte file that's in whatever text format it is, you can load up a piece of it and then compute what's going on with it, find the next line break, and then start at a line and continue processing a record or something like that. That is figured that they don't have so much like other sorts of things to do this. Some of the processors, they'll have some string instructions, and their idea will be to find like, I will thrash memory and find the end, or these sorts of accounts. And so they do have kind of like find first set or bit scan forward. They will perform. It's optimized and it's built into the hardware to do some of the repetitions or these things to still keep kind of branchless and if not stallless, is like stalls less. This is the idea. But otherwise, though, these are the instructions that there are, and then it should be just a regular kind of routine to build this up and out, because everybody uses ASCII all the time. And in the higher level languages, it's just so common that everybody knows that, for example, a given character's hexadecimal value is its numeric value, like OX20 or 32, is that space or something like that, or where A starts, or that A, the uppercase letter, and A, the lowercase letter, are just separated by a given value, and so you can just subtract A from A and get, or subtract a constant A from A and get the lower uppercase to compute 2 upper or 2 lower and these kinds of things. Vis-a-vis is upper and is lower and these kinds of things. So that's just, since talking in the previous talk about the SIMD instructions, or single instruction multiple data, then that's kind of getting into the ideas here of the vector-wide scalar word, which is a bit more about doing parallel operations to achieve serial algorithms. And then those could be parallelized as well, is also its own sort of account. But that said, then it helps describe then with regards to having multiple finders, and then trying to figure out multiple matchers and these kinds of things, that it can just compute a whole ton of these in this NFA, or for the DFA and the NFAs, that it makes for an account of the NFA that is, as written as the DFA, it's got lots of redundant looking edges, or instead of machines with their states and transitions, it's kind of like the arcs that make the plants from these findings, the matchings, and then these as the acceptor and rejector logic goes along, and then for mismatches and made matches, then as the intersection and union of and set minus and complement of these things are to be composed from expressions like regular expressions or expressions that describe a grammar, then their productions result, the recognitions or the recognizers and their productions. That this sort of machine is so briefly described here on its own account. Then how to break that across the words? There is sometimes a value will straddle the 64-byte its boundary. So for example, if the word cat is like at the last offset, its first letter, and then it continues into the next block, then the idea is in these partial accounts, there's basically for straddles, there's splitting and stitching. So the idea is that the state machine, as the sole model of the parsing and grammars, as it's going along, it's in the general purpose registers next to these vector registers. It's keeping track of the offsets. For example, it's laying those out in another copy of the data. It's like, well, we're not going to modify the original data, but we're just going to have as much scratch for it underneath it for each one of these register accounts, when we're going to persist that and then use that as a computed view of the contents of this file. So the straddle is when it's detected. It's like, well, I've reached the end of my data and I'm not sure whether it's a made match or a mismatch. So then it's just tear the whole thing down, load up a new piece of data, keep the state of where it is, and then the registers just get rolled and shifted back and forth. It's like, just like when you're loading from an unaligned memory location, or you can't go past an aligned memory location, then you can kind of just, well, load that up, and then we'll just shift the offsets back a bit or shift them forward this way. Then the straddling and the splitting and stitching is then just part of the usual account, that it uses the same intermediate data format and uses the most usual sorts of logical operations that there are on the thing. So that's a brief description of an application of single instruction multiple data for serial algorithms for the recognition of text and binary files. Well, that's the hour. That's Reading Foundations today. Reading Foundations faster.